Hello, everybody. It's a pleasure to have here today Mike Boylan-Kolchin, who kindly accepted our invitation to talk at the CosmoVerse series. Mike is currently Associate Professor at the University of Texas at Austin, and previously he was a faculty member at the University of Maryland and a postdoc at the University of California, Irvine and the Max Planck Institute for Astrophysics, while he earned his PhD at UC Berkeley. Mike's research topics are theoretical cosmology and galaxy formation, especially near-field cosmology, small-scale structure as a proof of dark matter physics, and more recently, globular clusters in cosmological context and physics of the high redshift universe. Today, he will present the cosmological tensions in JWST era. Mike, you can start, please, when you're ready.
Okay, thanks very much, Eleonora, and thanks for the invitation and for everybody for coming. Yeah, what I'd like to talk about is sort of how JWST is changing our picture of the high redshift universe and how that might be putting tensions into additional tensions on the ΛCDM cosmology, or maybe telling us something else about galaxy astrophysics, or maybe more mundanely the instruments themselves. But of course, that's very important for understanding them overall. So I think any talk like this, contractually, you're obligated to start with the ΛCDM model coming from the Planck data and the Planck temperature power spectrum. Of course, this is kind of a stunning success at some level. We observe these fluctuations at a part in 100,000 in the temperature maps. And with the standard line is with 6 parameters. You can map this extremely well, and you see the 6 parameter fit is an extremely good one to the power spectrum that we see here. Of course, I think it's worth saying, I won't say too much more about this, but of course, this fits all the data with only 6 parameters if you sort of have your hidden parameters kind of in the background there. So you have to enforce spatial flatness. You have to assume that the CMB temperature has been measured accurately. You have to fix a value of the effective number of relativistic degrees of freedom, specify the neutrino masses, the primordial helium abundance. So, but regardless, I think even if one sort of thinks about these as these nuisance parameters, it's still pretty remarkable that the very early universe can be described extremely well with basically these 6 parameters. So 2 densities, the baryon and cold dark matter density, 2 numbers that describe the spectrum of density fluctuations, so the sort of amplitude and the slope of that power spectrum. You have the angular size of the CMB sound horizon and the optical depth to electron scattering. And so those are the parameters that basically tell you everything about the early universe in this theory. But of course, we want to think about not just the early universe, but the later universe, and we want to think about different scales. And so just as a thought, the first peak in the CMB corresponds to roughly 100 H inverse megaparsec physical sound horizon scale. And that's much, much larger scale than any kind of galaxy scale physics we're thinking about. The largest objects that we think are virialized today, galaxy clusters, might come from a region that's roughly 10 times smaller than that in terms of initial radius of fluctuation. So that would correspond to a multipole moment of 3,000 or something, a galaxy cluster of 10 to the 15-ish solar masses. And if we're thinking about things like the Milky Way, that's up by another factor of 10 in multipole moment, so multipole of 30,000 or so. Of course, the fluctuations are highly damped there, and we don't get to learn about anything from the CMB on those scales in particular. And probably more importantly, those scales are not in the linear regime today, they're in the nonlinear regime. So we don't see small density fluctuations, we see very large fluctuations from point to point on scales that are the mass of the Milky Way, or even up to something like galaxy clusters. So the nice thing about this ΛCDM model is that with the same 6 parameter model, we can actually understand the evolution of density fluctuations in the linear regime. So we can take this initial density fluctuation of order of part in 100,000 for perturbations entering the horizon at the microwave background era, and evolve it with linear theory to any later time. So this would be a slice of the universe, the density field extrapolated to redshift of 127, which is maybe where you'd start an n-body simulation using linear theory. And you can go all the way to redshift 0 with linear theory, okay? And so linear theory is very handy, and that's completely specified, again, by general relativity and the 6 parameters of the ΛCDM model, basically. But if you want to look at the nonlinear density field, you can't just do this. You need something more. And a reminder, the nonlinear density field is very different from the linear density field. So I can flash back and forth between these two. This is the extrapolation of the initial fluctuations using linear theory to the present day. This is the evolution of that same density field using cosmological simulations, so supercomputers that actually can track things into the nonlinear regime. And you can see some sort of correspondence a little bit. There's more mass here, there's more mass in the initial, in the linear theory prediction, but things go very different, of course, once you're in the nonlinear regime. So ideally, if we want to study galaxies, we have to learn about the nonlinear regime, and generally that does take big computers, lots of computing power. There are certain uncertainties there that we have to understand. But a nice aspect of cosmology is that we have something like extended Press-Schechter theory that tells us the statistics of the nonlinear density field can be computed from linear theory. And we can compare this to simulations and find pretty good agreement, actually. So if we want to understand how many collapsed dark matter halos are there, how many perturbations as a function of mass are there, we can do this actually from linear theory. All right, so you have the RMS amplitude of fluctuations as a function of mass. So this is basically just plopping down spheres that contain on average mass m at redshift 0, and asking what's the variance in the masses you measure from point to point in the universe. On very large scales, of course, that variance is small. It better be 0 on the largest scales, essentially. And on very small scales, it's a high variance. You might be in a galaxy, you might be in a void, right? And there's very large density contrasts. So linear theory tells us when things collapse on average, and that's when the fluctuations cross a certain density threshold. Okay, that threshold is of order unity. And that gives us a nonlinear mass today, a characteristic mass in the universe for a nonlinear structure, which is where this fluctuation crosses the collapse threshold. And today that's of order 10 to the 13 solar masses. So in the universe as a whole, you can think of things being typically in the linear regime if they're on much more massive scales than this, and typically in the nonlinear regime if they're on much smaller mass scales than this. Right, so with this then, we can actually directly predict, just using the linear theory, the 6 parameter ΛCDM model, what we should get for mass functions of dark matter halos, or for statistics of the nonlinear density field. And we do that by basically asking, okay, at a given mass, we don't just have one amplitude of fluctuation, we have a whole distribution of fluctuations. So we consider how rare a peak is at that mass. So basically how far an excursion it is away from the RMS value that you'd get. That is to say, there are collapsed objects that are more massive than 10 to the 13 solar masses today, but they have to be rare tails of the density fluctuation. And so we measure that by the peak height, and that basically just tells you how far away you are from this line at redshift 0, let's say. And so for 10 to the 15 solar mass halos, this is sort of galaxy cluster mass scales, they're 3.5 sigma peaks in the density field. So that means they're quite rare, and their abundance is then suppressed by this peak height, and exponentially suppressed by this peak height squared. Okay. And this is all coming directly from Press-Schechter theory. So again, we can compute the statistics of the nonlinear density field from linear theory. And that tells us the number density of dark matter halos as a function of time. So this is the cumulative number of halos per unit volume as a function of halo mass at several different redshifts. You can see, let's say the Milky Way would sit here at 10 to the 12 halo mass. So we would not have anything anywhere close to the mass of the Milky Way in dark matter until, let's say, redshift 7 or something. And even then, there'd only be one per 100 or per 1 million cubic megaparsecs. So they'd be very rare. We can also compute the total mass contained above a given halo mass. And I'll be using that because that can be related to the total mass in stars we see today. Okay, so then going back to the idea of why JWST is helpful for this, if we ask, what do we understand about the universe? Well, Hubble has been able to probe galaxies out to about redshift of 11. This is the famous GNZ 11 galaxy, which was measured by Hubble to have a redshift of 11. It's actually just a couple of days ago. That was downgraded a little bit by JWST, and I'll show that spectrum later. But basically, anything from redshift, anything higher than redshift 11 is something that we don't really know about in terms of statistics of the collapse density field as probed by galaxies. Right? We need to have something beyond the Hubble Space Telescope. And of course, this is where JWST comes in. And we're interested in this because this is where the first galaxies should form. And this is where the rare peaks in the density field that might probe this ΛCDM cosmology would actually be testable. So JWST is optimized to push the high redshift frontier for galaxies because its infrared coverage captures the rest frame UV, which is basically hot young stars, redshifted from redshifts 10, 12 or higher. Okay, so basically O stars are the dominate young stellar populations. They emit very strongly in the ultraviolet. That's redshifted into the infrared if the galaxies are above redshift, let's say 7 to 10. And so that allows us to observe their light with JWST. So JWST turned on, and the first results were pretty stunning. So the expectation, I think, was that, okay, the first observations will help us understand maybe the NIRCam instrument, which is the main imager people are using, probably find galaxies at a distance seen by Hubble at redshift, out to redshift 10, or maybe just beyond. But there'd be a lot of work that would be required to get out to significantly higher redshift. And if you were not under a rock or something last July, August, you saw there was a huge amount of data that came out and a huge amount of discoveries. I would say a shocking number of galaxy candidates that were quickly discovered. It was claimed out to redshift 20 or so. So we're talking 200 million years after the Big Bang. So pretty amazing stuff. The press got wind of this very quickly, of course, and so there are a lot of articles ranging from, I think sort of fairly prosaic, so unprecedented, unpredicted bounty of bright galaxies in the early universe. So that's, I think, fair, at least galaxy candidates. And then there's also things saying JWST's first glimpses of early galaxies could break cosmology. So that's a little more breathless, but also potentially true and very exciting, right? So these first data were really interesting. One of the things that was most interesting to me wasn't, well, I thought these very high redshift galaxy candidates were extremely exciting, but to me, one of the most surprising results is seemingly very massive evolved galaxies at slightly lower redshift. So sort of the edge of where Hubble would have been able to see, redshift 8 to 10, let's say. There were claims of galaxies that were of order 10 to the 11 solar masses at that time. Just for context, the Milky Way is around 6 times 10 to the 10 solar masses today, okay, in stars. And so if we ask what it would have been like back then, well, we don't really know, but maybe the main progenitor would have had 10 to the 7, 10 to the 8 solar masses in stars. So we're talking about things that could have been 1,000 times more massive in stars than the progenitor of the Milky Way at redshift of 8, 9, 10. So this is pretty remarkable. These are not pushing the redshift frontier, but they're pushing the mass frontier in a certain way. And so this is from a study by Ivo Lebet and collaborators. And I think one of the ways they show that this is kind of remarkable is that the stellar mass density contained in these objects is far, far beyond what you would have expected based on extrapolations of previous HST results. So the purple lines here show you what was found at what one would expect based on extrapolating HST results from redshift 8. The red line is at redshift 10. And you can see their measurements are actually, well, they're way above the redshift 8 lines already, but they're thousands of times above the redshift 10 extrapolations. So if these results are correct, right, this would imply thousands of times more stars per unit volume in the high redshift universe than was expected by Hubble. So the reason I gave some of this introduction about doing predictions of the nonlinear density field from linear theory is that we can actually understand what we should have expected based on the ΛCDM model or some upper limits. So what can we expect? Well, if you take a given amount of dark matter, it comes with a given amount of baryonic matter. The two are well mixed in the early universe. And so there's a cosmic allotment of baryons that each dark matter halo has, that each collapsed object has. And that's just the universal baryon fraction, so omega baryon over omega matter, something like 16%, times the halo mass. Okay, and so that allows us to say, if we have a halo mass, that gives us a maximum stellar mass that could have formed in that halo. That is, given that halo mass, we know how many baryons there are, and the number of stars better be less than the mass in stars better be less than the mass in baryons. So we can talk about a conversion efficiency of baryons into stars. That's this epsilon star, and that better be less than 1. You can't convert more. Get more mass in stars than you actually have baryons in your dark matter halo. So this gives us a way to map from a halo mass to a maximum possible baryonic mass. Or if you want to think about it the other way, given a stellar mass, this gives you the minimum possible halo mass you need to be able to create that amount of stars. You can do this for number densities. And you can do this similarly for mass densities. And that's what was plotted in Lebet et al. That was so discrepant, the stellar mass density, so the mass per unit volume. Right. And so when I did this, I found something pretty surprising, at least to me. And that is that you basically require more stellar mass than you have baryons in these dark matter halos. Okay. So it implies that you've converted more of than your available baryons into stars. Remember, this sort of upper limit is epsilon of 1. That's a hard upper limit because you just can't convert, you can't create stars out of nothing. And I should also say that our expectation is that epsilon is pretty low on average in the universe. So for example, at redshift 0, this average epsilon star peaks at around 20%, so 0.2 for Milky Way mass halos, and it's much smaller for bigger halos and for smaller halos. So we expect maybe to see epsilon of 0.1, something like that, if present day galaxies are representative of anything like this. And the galaxies from the Lebet et al. Sample live in this region, the excluded region here. So again, this is just taking up the expected mass in baryons that are in halos massive enough to form these galaxies and saying, holy cow, there's actually more stars than available baryons in these systems. With those results, you can also figure out the implied number densities. And if we assume that all of the baryons have been converted into stars, with the original numbers from Lebet et al., we find that these things basically have implied number densities of maybe 10 to the minus 8 per cubic megaparsec to 10 to the minus 6. So this is exceedingly rare. You'd have to survey hundreds of millions of cubic megaparsecs to see this. And for context, basically these early results came from 100,000 cubic megaparsecs. So you have to survey, you would have expected, thousands of times more volume to find something that's this rare a peak in the density field, basically. Okay. And the result, it gets much worse if you assume that this epsilon star is less than 1, which it probably should be. That moves all of these theoretical curves down, and then that makes these objects all the more rarer, okay? Because if epsilon star is lower, that means for a given baryonic mass, you need a larger dark matter halo mass. So you're probing even further out in this exponential distribution. So the problem here is that the early JWST data implied more stars than there was available material to make stars in the ΛCDM cosmology. So the implications of this are that either the inferred galaxy properties are wrong, we got very lucky or unlucky, as you may want to look at it, and observed a very atypical portion of the universe, or there's something in the cosmological model that would need updating. And so I'll kind of try to walk through each of these possibilities. So with the galaxy properties being wrong, the first possibility is that the galaxy properties are wrong because the observations are sort of air quotes wrong. So I won't say that the observations are wrong, but the observations need to be calibrated. So basically NIRCam has several detectors, and the detectors have independent calibrations that need to be determined sort of in flight, right? And so basically to understand how the 0 point of one detector is relative to another, need to take observations and figure out what that offset is. And so the original data that people were using used something like this for the 0 points. And what I'm showing here is the color magnitude diagram of a simple stellar population. This is a globular cluster. So the globular cluster should lie as basically one distinct sequence in here. What you're seeing is several sequences, and the sequences are coming from different chips on the detector. This is basically saying the original calibration of this detector wasn't quite right. You need to apply some kind of offset to understand the sensitivities of the relative parts of the detector. So that's one thing you can do right away, and that causes some shifts. This is a 10 to 15% level effect. And using these kind of corrections, people are now able to figure out what the calibrations are much better, okay? And so this does have an effect on the original results. So if I take the results from before, and now I look at the second version or the latest version, you see that the stellar masses are still quite high, but they've actually come down a little bit. So the plotted limits are a little bit different here. Here it cuts off at 10 to the 12 solar masses. Here it goes a little above. But things have come down by a little bit in these latest results because of this calibration, largely. So what does this mean for the tension that I was talking about? Well, the tension is decreased, but I would say it's still present, certainly. So this is basically saying you still need to convert 100% of your baryons into stars to be able to reproduce the mean of this observation. If we consider sort of all sources of errors that they've thought about, that's in the mass estimates, in sample variance, Poisson noise, everything that gives you this error bar here. And again, this is still either consistent with being in the excluded region or sort of well inside of this epsilon equals 1, this maximally efficient conversion region. But even this data point here, if we take the low error, is extremely high, okay? So remember, epsilon of something like 33%, that's this sort of orangish line, that would correspond to something that's more efficient than the most efficient galaxies we see on average in the low redshift universe. So even if this doesn't 100% break cosmology in an obvious way, I think it clearly says that something's going on very differently at high redshift at the very least. in the fact that galaxies are forming extremely efficiently and potentially does still have this issue with the overall cosmology. So if we ask how that changes the implied number densities of these objects, remember before these had implied number densities of something like 10 to the minus 8 per cubic megaparsec or so. Well, now they've moved down. There's something like 10 to the minus 5, 10 to the minus 6 at the very least, if this epsilon is 1. If the epsilon is a little more reasonable, something like 0.3 to 0.1, we're still talking about things that are exceedingly rare. Let's say 10 to the minus 8 per cubic megaparsec. And again, so you'd expect you'd have to survey 10 to the 8 cubic megaparsecs to see one of these. And the initial surveys are only about 10 to the 5. So you're talking about a factor of 1,000 difference in the number predicted versus seen. Okay, if we ask about the peak heights, how rare are these? These sit at a peak height of 4.5 at the very least. That's if this conversion efficiency is 1. Okay, and if the conversion efficiency is lower, they sit at even rarer peak heights. And just for comparison, a peak height of 4.5, which is the minimum these would sit at, is a halo that would be among the most massive galaxy clusters we observe in the universe today. That's the equivalent scarcity of these objects by mass, I'd say. Okay, so what else could be going wrong here? Well, remember, we're not observing stellar mass, unfortunately. Well, we'd really like to do that. What we observe is light, and we need to figure out how to convert that light into stellar mass. So that depends on how you assume the stellar mass is distributed across the mass spectrum of stars. It depends a little bit on how you assume the stars have formed, several other things. So for example, if you assume that there's a certain amount of very massive stars relative to very low mass stars, and your light is dominated by those very massive stars, if you change the number of low mass stars which dominate the mass, that can really change the conversion from the light to the mass. Okay, so that's certainly one thing that's going on there. Another thing that's going on is we have to make sure we're measuring the galaxy redshift correctly. So there's been a lot of discussion about whether there's confusion between these galaxies at maybe redshift of 10, these galaxies candidates at redshift 10 or 12, and galaxies that could be at much lower redshift. The reason for that is that most of the observations that people have taken so far are just photometric, so that's just based on imaging. So you have data collected at a series of points, let's say, by these NIRCam filters. And what you're looking for is the galaxies to be detected in the redder bands, but not in the bluer bands, because the light blueward of Lyman alpha has been completely absorbed by the intervening intergalactic medium. And so that's what people see in these kind of spectra. So again, this isn't a spectrum, this is the photometry. But you can see put a model spectrum on here, and this is what you'd expect for a galaxy at high redshift, redshift 12 or 14. It would have this blue spectrum, okay, and that fits with the detections in the redder bands and the non-detections in the bluer bands. But they're also showing that you could get something similar if you have a very dusty galaxy at much lower redshift. And so understanding an actual redshift for these galaxies is extremely important. So are these star-forming galaxies at very early times, or are they quiescent galaxies at what apparently is now low redshift, redshift 5? When I started out, that was unbelievably high redshift. So I guess that makes me old rather than anything else, but it's pretty cool to see how this field has been advancing. So I think hot off the presses is that we're able to actually get spectroscopy. I shouldn't say we, it's sort of including myself and people who are doing all the things. I haven't done anything on this front, so I can't claim any credit. These are amazing data. This is from the JADE survey, so there are a few papers on this already. 4 galaxies, the highest redshift of which is redshift 13. And the mass for these things is of order 10 to the 8 to 10 to the 9 solar masses. This is the kind of spectrum you can get. So this is pretty stunning. This just came out very recently, this week actually. This was the highest redshift galaxy known in Hubble. It's got a spectrum from JWST now, and it can be very well measured to be a redshift 10.6 galaxy. You can measure this break at Lyman alpha here, so no flux blueward of Lyman alpha. But you can also measure very easily oxygen lines, magnesium lines. You can measure even neon, various other lines. So this is pretty stunning, and there's no way to mess this up, to mix this up for a low redshift galaxy. So as more and more of these galaxies are actually targeted with spectroscopy, we'll understand this better. But again, you can't really do that until you found the candidates to target with the spectroscopy. So in the first pass, nobody actually knew where to look for this. The reason people took these spectra was this was already a known galaxy with Hubble. So for the systems I was talking about, I think we have to kind of wait and see. If I ask where these galaxies that are spectroscopically confirmed fall on the plots that I was showing before, they're kind of here-ish. Okay, so they are significantly sort of less cosmologically tense, or in less cosmological tension than these galaxy candidates are over here. Okay, so they sort of sit in halos that are number densities of 10 to the minus 3 at the very most, and maybe 4 sigma peaks in the density field. So what are some other possibilities for the tension? So the observed portion of the universe could be highly atypical. So people with the first JWST surveys only looked at a small region of the sky. The JWST footprint is basically much smaller than the full moon, and so that's what people are staring at. And so if those observations just happen to be in a very overdense portion of the universe, then this issue would go away. But the naive expectation is you need to survey hundreds to tens of thousands of times more of the universe to have seen these exceedingly rare and massive galaxies. So just as I was saying, this is sort of the scale on the upper right here of the NIRCam footprint relative to the full moon. And so I think that the exciting thing that's going to be coming online soon is that the Cosmos Web program will actually be surveying much larger region. So we'll have a much better understanding of the statistics of these objects. So are we looking at rare portions of the universe, or are we finding galaxies that are unexpectedly massive? So if every other possibility gets exhausted, so if it's not a question of galaxy properties, and it's not a question of the rareness of these objects in the universe, we have to start also considering whether there could be an issue with the successful cosmological model. And again, I would say that that's a very high bar to clear. The cosmological model is very successful, right? So what you need is faster formation of cosmological structure at early times, so more faster structure formation. And there's basically no room for this in a base ΛCDM model, in that 6-parameter model that I was talking about. So all the parameters are known to 1% precision or better. There's no wiggle room. But if you have extensions to this model, then you might get something that can work. And the extensions that you need are things that have a higher matter density. That gives more sort of overall matter in the universe. A higher normalization of the matter fluctuations, so a higher sigma 8. And also, if you have a spectral slope that is larger, that means that for a given observation of the density fluctuations in the CMB, you'll actually have larger fluctuations on galaxy scales. So all of these things would go in the right direction if you could find something that has higher values of the matter density, sigma 8, or the spectral index without ruining the agreement on larger scales. So one possibility that does this is a short period of early dark energy at redshift of 3,500 or so. So this has been discussed in a number of papers. So there's, I think, well, people on this call are much more of an expert than I am on this. But this was originally motivated in large part because of the Hubble tension. So early dark energy actually changes the implied value of the Hubble constant, as I'll talk about. But this would do the same thing for the for our expected values of the amount of mass that could have formed by a given redshift. So the idea here is you sort of now have a 9-parameter model where you have a few extra parameters for early dark energy. And if you fit then the full data sets with CMB data sets with this early dark energy model, you find that you do in fact get a higher matter density, a higher amplitude of fluctuations, and a higher spectral slope than for the base Planck models. And I don't want to get into too much whether there's actually hints for this in the ACT data or not, but there's a lot of discussion about that, and I'm sure there's actually been discussion here probably about all of that already. What I wanted to talk about, though, is how this affects structure formation. So this is from a paper by Anatoly Klippin and collaborators that shows you the difference in the power spectrum of an early dark energy model relative to a standard lambda cold dark matter model. And you can see all of these parameters that I was talking about lead to more power on smaller scales. Okay, they actually lead to more power on basically all scales. But the important thing is especially these sort of smaller scales here, K of let's say 0.5 and larger. Remember, what we're thinking about is that the number density of these dark matter halos scales as the scarcity of these objects. And the scarcity of these objects depends on the amplitude of fluctuations, sigma. And so if you have a higher sigma 8, you're actually able to get to a higher amplitude of fluctuations earlier. And so that means these halos are just less rare. You're able to get more structure at early times. So a way to look at that would be just they ran an n-body simulation and counted up the number density of objects in early dark energy compared to lambda CDM. And you can see while at redshift 0, they look quite similar. As you start going back in time, you start finding that in the exponential tails, you're getting a substantial deviation from what lambda CDM predicted, the base lambda CDM. You can get several, here it's up to a factor of 2 more halos at a given mass. And as you go even earlier times and you're probing further out in the exponential tail, this can be an even larger effect. So if I go back to this kind of plot that I had shown earlier, and I ask what would happen to these curves, these expectations from lambda CDM in an early dark energy model, well, oh, sorry, wrong direction. These would basically shift up these curves by a factor of 3, and it would be somewhat easier to accommodate these data points in this kind of model. And again, you have a larger baryonic reservoir. All right, you also have more of these objects that have collapsed, and so you're able to accommodate these kind of halos more easily in an early dark energy model. And I don't necessarily want to single out early dark energy as being the right one, but I think that all of the models that would do this, and again, all of the models that will solve the Hubble tension probably with early universe physics, are ones that are ending up with higher matter densities, sigma 8 values, and or spectral slopes. So these are kind of generic solutions that can give you a good fit to the CMB still while adding certain physics in the high redshift universe. This is the direction that those parameters would change. And then this is the direction that would go, it would sort of promote more early structure formation. Okay, so of course, as I mentioned, the main motivation originally for early dark energy was that it can resolve the Hubble tension. This is just one of the nice figures from Adam's recent paper on this that shows if you take the Planck value and the Shoes calibration of the local Hubble constant, then you get this very strong discrepancy at greater than 5 sigma. And if you remember that basically we're getting that early dark energy is helping this by changing our inferred sound horizon. So remember the CMB very accurately measures the angular size of the sound horizon. And so what you need to do is keep this angular size of the sound horizon the same. And so if you reduce the physical size of the sound horizon, r star, you need to reduce the distance to the sound horizon. And the way to reduce the distance by the sound to the sound horizon is by increasing this Hubble parameter at redshift 0, right? So if you have faster expansion in the very early universe, that gets you to decoupling faster. So you get actually a smaller sound horizon. To compensate for that smaller sound horizon, you need a smaller distance to the CMB, and that requires a larger Hubble constant. Now, one thing that I think people haven't talked about as much with respect to this kind of solution, and in general, early universe solutions again, is that this monkeys around a little bit with our understanding of time in the universe. So I just thought I'd spend the last few minutes coming back to this point, which is that, you know, the age of the universe is very precisely known in the Planck cosmology. So if you assume the Planck 2020 base cosmology with 6 parameters, the age of the universe is known to 0.2% precision. So 13.8 billion years with an error of only 20 million years. And remember, there's no way to actually measure the time cosmologically. What you measure is an integral over the expansion rate. So this is basically saying once we know the expansion history, we can calculate the time. But the expansion history changes, of course, if you add early dark energy. That's important because that's what you want it to do. You want it to change the expansion history so that you can solve the Hubble tension. But this then feeds back into this integral, right? And that changes the relationship between time and scale factor, or time and redshift. So anytime you change the implied composition of the universe, you change the connection between when something happened in time and when it happened in redshift space. So for the age of the universe, Planck determines this extremely accurately. I think Shoes is agnostic about this. Shoes calibrated Hubble parameter. But if you ask what these sort of standard early dark energy models would find, well, they actually get an age of the universe that's substantially different, okay? So you get down to something like, well, maybe up to a gigayear younger, so 12.8 billion years, if early dark energy is the right explanation for the Hubble tension. So what this would mean is that a fixed look-back time would correspond to different redshifts. So if I ask what a redshift is in an early dark energy model and say, let's say redshift of 2, that would correspond to about 10 billion years ago. In a Planck cosmology, it's pretty close to the same redshift. It's a little younger. But if I ask what corresponds to, let's say 13 billion years ago, well, that's redshift 12 or 13 in an early dark energy cosmology, and it's only redshift 6 in a Planck cosmology. So at small look-back times, the redshift corresponding to a given look-back time is about the same. At large look-back times, the redshift in Planck is much smaller than the redshift in early dark energy. And again, that's just because the whole timeline is kind of compressed in an early dark energy model. So this says if you have something that you know formed at a certain time, that would form at a very different redshift in these kind of models. So for example, a hypothetical star cluster that you know is between 12.5 and 13 billion years old, you can say in a Planck cosmology, it must have formed at redshift 5 or so, but in an early dark energy cosmology, it must have formed much earlier in the universe's history, in some sense, in the redshift space, it would have formed a redshift 10, something like that. And one important point here is that these are kind of completely disjoint regions, right? So you're really saying the time when this happened in the evolution of the universe is very different in these two kinds of cosmologies, even though the parameters aren't that different, I'd say. And everywhere you look, you find this mapping between redshift and look-back time. So if you look at the cosmic star formation history, or how stars have formed in small galaxies as a function of time, you always see, okay, on one axis, there's a look back time, and a corresponding axis, there's a redshift. This correspondence requires understanding of the underlying cosmology. If you start changing that, you start getting things that are different. So, I mean, what I'd say is that given the Hubble tension, if we take it seriously, and I know most people are taking it at least somewhat seriously now, then there's an irreducible uncertainty of at least something like 5% in the relationship between redshift and look back time. So the age of the universe probably isn't known to 0.2%, but it's known to something like 5%. And that's because it's not just a question of how well does this one specific model fit the data, it's a question of how well do different models possibly fit the data. So there's a systematic error potentially of up to, sorry, this shouldn't say 0.1, this should say 1 gig a year here. Okay, that's a big difference. So, we're talking about something that's an error that's inflated by a factor of 40 or something relative to the precision. So this is an accuracy issue. So you might ask, do we have a way to measure the age of the universe or any age independently of this? And I think the answer is yes. And historically, this is the way that people did things. The universe better be older than the oldest objects you can find in it. And if we look at the oldest things we can find, well, if there are very low mass stars that form right after the Big Bang, as long as they're less than about 7/10 the mass of the sun, they should still be around today. They should still be on the hydrogen burning main sequence. And so if we can find very old objects like this and measure their ages, then we can set a lower limit on the age of the universe. And again, historically, a good place to do this is globular clusters, which are just collections of ancient stars. The key, though, is that they're sort of single stellar populations, okay? So this is sort of the HST image of a globular cluster, the very central region. They're about, let's say, 100,000 to maybe 10 million coeval stars. And so that means if you just think about them as how the stars burn through their fuel, there's a direct relationship between the lifetime and the mass. More massive stars burn through their fuels faster. So something like a 12 solar mass star might burn through its fuel in 10 million years. These very low mass stars, again, have lifetimes that are definitely longer than the age of the universe. And so what you'll see is the older a system is, the fewer of these high mass stars in the upper left it'll have. They'll all have died off. And so you'll see these stars evolving from the main sequence. So for example, here is a cluster that has a lifetime of 14 million years. You see its stars have turned off the main sequence. Here is something in sort of cyan that's maybe 100 million years. Here's a galaxy in orange that we think is 7 billion years. And a globular cluster that's 10 billion years would have a turn off that's even lower here. Okay, so people have gone out and measured things measured the ages of globular clusters with Hubble. One of the key uncertainties is the distance. And so if you have a parallax distance, then you can actually figure out exactly the absolute magnitude of where that main sequence turnoff is. And that will give you the age directly. So this is what Tom Brown and collaborators did. And they found for this ancient globular cluster that has a well-measured parallax, it has an age of 13.4 billion years. There's a statistical uncertainty of around 700 million years. And there's still a systematic uncertainty of around 1 billion years. Okay, and that comes from understanding the parallax rest frame, and then from various things like how much extinction is there along the line of sight, and how well do you understand the stars themselves. But just again, to put this in context of the Planck cosmology and early dark energy, this I think would be pretty compatible with forming a few million years after the Big Bang in a Planck cosmology. In an early dark energy cosmology, you're starting to get to a place where you have to assume that these objects are systematically younger than the mean age in order for things to work out. So this younger age of the universe in early dark energy, and in general, in pretty much all of these solutions that change the expansion rate at early times to solve the Hubble tension are going to give you these younger ages. They might start being in tension, especially if we can knock down these uncertainties. So that's why we've kind of embarked in a program to look at this. Brian Chaboyer was one of the first people to do this in the 90s with the stellar models that people had then. But then, of course, with precision cosmology and the CMB, people sort of stopped worrying about getting ages of stars to measure the age of the universe because the precision was just much worse. But now we're in a new era with lots of large surveys of stars. We're also able to do the MCMC exploration of parameter space a lot better for the stellar models. And so we're able to revisit these kind of absolute ages. So a cluster like M92, one of the oldest we think in the universe, we think has an age of around 13.8 billion years with an uncertainty of maybe 750 million years. So again, compatible with the age of the universe in a Planck cosmology, but in an early dark energy cosmology, it's starting to become a little bit troublesome potentially. And the dominant uncertainty here is distance, which I think is a good thing. So it doesn't really matter too much about the composition of the stars here, the nuclear reaction rates, the opacities, things like that. It's really just how well can we measure the distance to these objects. And so if we can reduce the distance uncertainties, then I think globular cluster ages can, again, sort of provide this cosmological context and provide an independent measure of ages. So just in terms of an outlook here, JWST is revolutionizing our understanding of the earliest phases of galaxy formation. I think we went through this wave of very striking early results where there was an enormous amount of data showing lots of high redshift galaxy candidates. A lot of those have either gone away or changed a little bit in their properties, but I think it's clear that there are a lot of galaxies out there at high redshift. Already there's spectroscopic confirmation of objects out to redshift 13, and so I'd expect that to only continue to be pushing the high redshift boundary in the coming months and years. And the other aspect of this that I focused on here is that there are these very massive candidates at 100 million, at sort of redshift 10 to 8, so the first 800 million years of the universe, which really are challenging our understanding of how galaxies can form, whether we actually understand the galaxy properties correctly themselves or the cosmological model. And the real issue is that you really need a lot more baryons in stars than baryons we think might even be present in these kind of massive halos to get these kind of number densities, these mass densities. So is it something about the masses? Is it something about the cosmology? I don't really know, but I think it's exciting to consider both of them. And the answer is going to be exciting regardless. So if it's something about the way we are doing masses in the early universe, that tells us maybe the stellar initial mass function is very different at high redshift, which would be very cool. If it's something about very, very efficient galaxy formation, that would be completely, I think, unexpected and something very interesting. And of course, if it's something about cosmology, that would be really cool. If it's something about cosmology, the direction the cosmological parameters would need to go with additions would be the same direction that go towards solving the Hubble tension potentially with, say, early dark energy. And so I think that you know, the prospects are really exciting in the next few years for making big progress here, because we already have observations over a wider area with spectroscopy. So we should know a lot more, I think, even in a matter of months on this. So I think it's a great time to be working on this and very exciting. All right, I think I'll stop there. Thank you.
Thank you so much. The very interesting and exciting talk. So we have already a question. Adam?
Hi, Mike. That was a really great talk, really comprehensive. I really enjoyed that. I think the the issue with JWST is particularly interesting because, as you said, it's such early days. This problem is likely to get worse as we survey more area and find even more massive, more rare objects than we can in a small area. But I wanted to ask about the issue of ages, because I've often been interested in this problem. my question is, what sets the sort of ground truth for ages? When I've looked at a lot of papers that claim to measure ages, they already assume a kind of a Planck cosmology and a correspondence between look back time and redshift. So their first principles are often already starting with, something that from the way you're looking at it, you wouldn't want to start with. And so my question is, also given uncertainties about, stars only use a small fraction of their available energy. And again, how do we know what that fraction is? How do you set ground truth for models that attempt to measure aging or the ages of stars? How do you do that without assuming Planck cosmology?
Yeah, I think it's a great question. And I think the way people normally do this, of course, is you have a bunch of different isochrones at a different age. So you assume, okay, for a given stellar population at 13 billion years, here's how something would look. At 14, it would look like this. And as you say, a lot of people, and I would have been one of them probably a few years ago, would have said, hey, why we don't want to consider 18 billion year old isochrones because that's clearly excluded by cosmology. But at this point, probably you want to include those in your fitting, even if it's just to say, well, what would be pushing me into that part of parameter space? What would be demanding an 18 billion year old stellar population for these objects? So I think what's saying the ground truth here is really a question of what's the sort of stellar physics. So I think you can create all of the isochrones, then just ask, we've gone out to, I think, 15 or 16 billion years with these isochrones. And really just asking, what do you actually get? What will give you agreement with the observations? And you really find that you don't need to go that very old. And it's really the variation of the stellar parameters doesn't seem to be that important. But I agree that it is hard to establish an underlying ground truth. And I definitely agree that you don't want to sort of set a prior on your age that's
right. But once you're using these isochrones, they already bake in sort of a correspondence between age and stellar evolution that involves uncertainties of, like I said, what fraction of the sun's going to use 10% of its energy. The sun could live factors of many times longer than it will. We don't really know that fraction well. Don't you need some stars where you sort of know ages a priori to set these things? I mean, I'm afraid the isochrones already bake in what we want to know.
Right. So I think one good thing is the isochrones don't bake in the redshift time relation, right? You're right that they basically just, the only time that comes from them is nuclear reactions. They know nothing about the actual age of the universe. But you're right that they do have those kinds of assumptions. The only star that we really know very well its age is the sun from radioactive dating of meteorites and things like that. So I think that that there still will be some kind of systematic uncertainty probably there, and I think that's maybe is going to just be an issue, and we have to figure out how to estimate what that systematic uncertainty would be, and so maybe the question is, can we ever get that to be competitive with this sort of 5% number where we are in cosmology? And I don't really know that right now, unfortunately.
Have we, maybe to rephrase it, have we learned something really interesting since, I mean, I remember when stellar ages used to be more like 16 gigayears, which is, off the table, but, have we learned something that's based more on, convection that tells us, here's how much fuel is used that actually changes those calculations?
Yeah, my understanding is that again, a lot of it, I think, is some of the distances were wrong for some of these systems, and that really led to the overestimate of the ages. But I'd have to take a look in a little more detail at whether there's something from the stellar physics side. There's nothing that I know of off the top of my head that's really changed fundamentally, though.
Thanks.
Thank you. Wendy?
Hi, yeah, that was really a great talk. Enjoyed it a lot. I wanted to ask if the models so far from which the masses are derived are based on what we know about the IMF locally. So something like Krupa or Chabrier. How much would you have to change the IMF to be consistent with what you would expect from ΛCDM?
Yeah, that's a good question. So I think that it's bigger than the difference, say, between saltpeter and Krupa and Chabrier. But I don't know if you're really saying, okay, we've got to do something that's totally wild and have, actually more of your mass is in the high mass stars than it is in sort of M dwarfs or something like that. I don't think you have to go sort of that far, but I think it is farther than just sort of variations among what people do in the local IMF. Now, I should also say there are variations that people do in sort of nebular line emission modeling and AGN lines, so there could be issues there. But yeah, I think it would have to be a substantial change. I'm not sure exactly what the level would be, and that's a good point. I should probably actually look into that.
And how would you tell if it changed? How would you know?
Yeah.
Right?
Yeah, I mean, so, some of the same authors, Van Dockum and collaborators, have actually argued that the change goes the opposite direction. Whereas if you look at the oldest galaxies around today, the oldest massive galaxies, they actually show a bottom heavy IMF is the argument, which would go in the wrong direction. There you have more mass per unit light. And so the conversion would be going the wrong direction if the archaeological evidence there is right. So I don't quite know how to put all these pieces together yet. And maybe I never will.
Yeah, early days, but really exciting data.
Yes.
Okay.
Thank you. Vivian?
Yes, thank you very much, Mike. Really, really nice talk. I was curious again, in your nice introduction, you mentioned that you're using the press-sector formalism that's based on linear theory. Any reason to believe that this could go wrong? And if it does not go wrong and we trust the linear theory, then could we turn the measurements of these massive galaxies into measurement of the linear power spectrum and say something like sigma 8 for linear cosmologists like me? Would you be able to measure sigma 8 from this data?
Right. So I think there are ways that press-sector can go quite wrong, I think. And so a lot of this is relatively calibrated off of numerical simulations. That's an important test. So it's not the sort of original press-sector. You do need to do some kind of extension there. So I think there is some potential issue. Actually, I didn't go into it here, but everything we know so far is that extended press-sector actually overestimates the abundance of these halos by a little bit. So these halos should actually be rarer than what I've been noting. And so the problem actually could be worse than what I've said, but I don't want to get into too much speculation on that. I think the hard thing about going backwards from this is that you don't really know which exact halos they've formed in, and so I think backing out a sigma 8 from measuring these will be hard. Now, that being said, the bias of these galaxies is so extreme that maybe if you can measure clustering of these objects, you can really differentiate pretty well among the actual halo masses that they're in. That is, in the low redshift universe, things maybe get up to a bias of 3 or 4, but these things could have a bias of 10 or something like that. And a slight change in the halo mass will lead to a large change in bias. And then maybe with the clustering, we'd have a chance at getting back to the linear theory predictions. I think that would be the best hope that I could think of.
Thank you.
Thank you. Neil?
Yes, a very similar and related question. I was wondering exactly about this kind of press-sector collapse formalism, and especially if you have tried also just using other kinds of mass functions like Chef-Dorman or newer ones like the newer fitting functions, and just tried out what happens if you use these kind of different functions. So basically the question would be if there's a second related question would be if there's any possibility of this being related to early nonlinear physics, because the mass, of course, is so high that the nonlinear regime might already be relevant for this.
Yeah, no, that's a good question. So I should say that we're not using press-sector. We are using Chef-Dorman. And so we're using things that are calibrated off of simulations, and basically the ones that are best calibrated at the highest redshifts, we think. And again, there it tends to be that those overpredict the mass function relative to n-body simulations by a little bit. And so, and as far as we can tell, compared to the best understanding of nonlinear physics, I've actually underestimated the scarcity of these objects. It would be good to play around a little bit with this and look at other mass functions. But again, most mass functions actually tend to predict, compared to I think you could just use an n-body simulation, for example, in a cumulative distribution, and maybe that would be a way to do this and understand rather than using a full parameterized version. So that might be a way to go about and do some of these calculations. And yeah, I think it is interesting to think about, could there be something in the high redshift universe that actually causes nonlinear structure to grow a little bit faster? I haven't thought at all about that, but that would be something that could be interesting in this context. Absolutely. I just don't have I don't want to, even though I'm a theorist and so I spend most of my time speculating without having any background understanding, this is one where I wouldn't even go there just yet, but just because I haven't thought about it at all, really. But I think it's a great question.
Thanks a lot.
Thank you. Erin?
Hey, Mike, thanks for the talk. Recently and Luso have been building the fourth rung of the distance ladder, right, using quasars, and they have a relationship that they assume. I've discussed this with Adam. They get strange results. They find that omega matter is larger at high redshift. We've been looking at type 1a supernovae, and we're seeing evolution between low and high redshift in type 1a supernovae within the lambda CDM model, which seems consistent with what they're saying, but we can't go as deep in redshift. So you're essentially saying that basically a higher matter density would sort of work for you.
Yeah, I think that's correct.
Right. Now, if you go back to the Friedman equations, it's a very easy argument to say that if the lambda CDM model is breaking down, H0 picks up zeta dependence. And once that happens, everything's running. It's a very simple math argument. So you do not expect omega M0 to be a constant. Basically when you start probing the lambda CDM model at different redshifts. This is essentially the comment.
I see. Okay, well, yeah, I'll have to. We exchanged an email about this paper that you're saying does this. So I'll have to go back and double check that. But that's good motivation for me to do that now.
Just
so
let
I
me
can understand that better.
point out that Menchi, I think it's Menchi and Nicola Menchi, who's he's been looking at the quasars and the overlap with, let's say, dynamical dark energy. So there certainly is work. There's overlap with your work, right?
Yes, definitely.
Okay, thanks very much.
Thank you.
Thank you. I think we have no more questions. So thanks a lot again for accepting the invitation.
Thanks very much, everyone.